welcome back to our small homestead here, our small farm. Today we're going to take a look at one of my, well, let's call it passion projects. In front of you there's the HTP Revolution 2500. The machine works really good, no complaints, except for one. When I got the 20-foot extension here for my MIG gun, the machine sometimes stutters. And the only reason that I can come up with that this happens, because this is a brand new torch, the liner should be perfect, even if it's entirely flat, is that the motor inside, the dual drive wire feeder, is just not powerful enough to push the wire at the correct speed over the 20-foot distance. Now, I might be entirely off. I reached out to the HTP folks, and unfortunately they ghosted me. And then I came up with this interesting idea that how hard could it be to take the wire feeder out of this machine and replace it with a 4-drive wire feeder, because that's what you have in high-end welding machines. I had this idea, I think, over 2 years ago, and I looked on and off. The wire feeder that is in here is a SwissFeed 150. You can see that from the parts diagram. And to upgrade to a SwissFeed 390 or 540, it's really hard to find shops that even sell these. So I kind of put that idea on hold for quite a while because I simply didn't find anybody who would sell one. And then by pure chance, I found a welding shop in Germany that actually does sell them. I bought an SF390, and then I ran into kind of a pickle because I told them I needed one with an encoder, and they sent me one without one and were like, if this is of no use to you, just send it back. And then I realized, well, how hard can it be to build an encoder for a motor? And in theory, it's quite easy, I thought. I'm going to show you a small prototype here. What I ended up doing, and I think it might work, well, we'll see. I never had this in there successfully, is this here is an A5047P. It's a magnetic encoder, very high resolution. It is connected to an STM microcontroller via quadrature encoding, and the microcontroller is connected to the welder inside. Why am I doing it this way? I don't know anything about the firmware of the welder. I think they have encoded welding profiles in the welder. I don't feel motivated at this point to start reverse engineering the firmware. I hope I don't have to. So my goal here is to build an electrical gearbox. Electrical because I need something that returns the same pulses per revolution as the old wire drive has, and at the same time runs with a totally different ratio. So the SwissFeed 150, I think, has 1:27 or something as a ratio. So one rotation of the gear that pushes the MIG wire requires 27 rotations on the motor. And the SF390 runs with 1 to 22.7 or 8, something like that. And also the wire drive rolls in here in the SF150 are like 30 millimeters. In the SF390, they're like 37 millimeters, right? So for this welder, with these programmed welding profiles, to work perfectly in synergic mode, it will only work if the pulses per revolution and the speed at which I get the wire does not change at all, right? So this here was a proof of concept just for me to understand, can I take the encoder that I built myself and translate it into the signal that this welder needs, right? And this might work. So anyways, this here was a prototype. Let me show you the real thing. This here is the real thing. You can see much smaller than the prototype. The reason why I couldn't use the prototype before was because the previous version was too thick, so I couldn't push it into the machine, right? So this is all the same you saw before, with a small improvements. Notably, there's a magnetic shield here. So this piece of metal sits there to protect the magnetic encoder from the magnetic field of the motor. And then it has a bunch of things that hopefully should make it EMI resistant, and it also has silicone coating, so hopefully it can survive inside the welder, because I think that's a very tough environment. I already crimped the right connectors to this for power. I just need to crimp these wires here, and once I have done that, we can open up the machine and install this, and then we can see if it works at all. Maybe this is a crock-pot idea and I just wasted a few $100s on it. Maybe it works great. Let's do this. I think there's one case in which this would not work, and that particular case has to do with the SF390 that I have takes more power. This is a 75 watt motor and the other one is a 50 watt motor. And the 75 watts, the way the speed here is controlled is with pulse width modulation. They basically turn power on and off really quickly. And if that is also tuned to the other motor, then this board here will have 2 slow start and 2 slow stop speeds. Now this here is a Molex Junior connector. They are great. They're very reliable when you use the right crimpers. Let me try to show you what I'm doing here. I'll walk you through some of the modifications I had to make to get that encoder to work. So usually when you have a motor with an encoder on it, the shaft that runs through the motor is slightly longer so that you can attach the actual encoder plate to it, or the magnet in my case. And when you buy a motor without an encoder, you get one with a short shaft. Which means, in my case, I had to drill through the plate of the motor and install the encoder. Maybe it's a little bit hacky. It's the only way I could get this to be seated in there. And then I took JB Weld and glued the magnet, the shaft. And then I drilled holes into the enclosure to make sure that I can actually position my magnetic reader above it. Because the A5047P is very sensitive to distance. It literally has to sit between 0.5 millimeter and 2.5 millimeters above the magnet. That was quite fun to get right. Time to open up the welder. Now obviously the warranty on that machine is already gone. Easy. All right. Now this can look very intimidating, and it still looks intimidating to me. So this here is the welder. Right. It's pretty much stock with the exception of one item. You can see here I added my own wire because getting to these connectors back there is actually quite painful. So I just added my own Molex micro in here, which is great because this way it's a little bit easier. Anyways, so we'll leave it open and then we're just going to run a no-load wire feed test here in a second. We're going to set this to 300 inches per minute and then we're going to run this for a second here and measure the outcome. Okay, this is about 6 seconds at 303. I'm going to actually cut it off because this way I have a reference. And then we're going to do another 6 seconds at the highest this machine can do, 629 IPM. Okay, another 6 seconds. The lowest is 59. So we have a mid-range, lowest and highest. 6 seconds on 59 IPM is actually not as low as I would have expected it to be, because if I have 303 IPM, I would have expected this to be a lot shorter than it is. Anyways, doesn't matter. Now I have what I need. We're going to shut it down, disconnect from power again, and I can run the same test again once we're done switching. Might be nice if you see something, eh? Maybe that's better. Now the one thing to call out here is that you can see I already did the dirty work of cutting out between the frames because, like I said, I already dry fitted this and it didn't fit because my 3D printed prototype case was just way too big. So now this thing here does not have that issue. It is certainly not too big. It shouldn't be anymore anyways. So let's get the torch off here. Now some of the things that are really nice here is like this here at the bottom. This is a push to connect fitting, so just put it out and you're already done with that. Now this one here I told you, the Micro Junior that I added in here, clip, and it's gone nice and easy. And then there are like 2 more connections which have to come out. The 2 up here, red, black, black in the back. Then there are 2 more which are like very unfortunately positioned, so it's very hard to see and even harder to film, honestly. Okay. Right. The original wire feeder is out. This should just thread in here nicely without any issue, so I can literally just take this and thread it back on. The compound here, to make it airtight again, I use this for everything: hydraulic lines, gas lines. So this is mostly in. The only reason why it doesn't fit right now is because you can see here this wire is rubbing, like the grounding cable. So I think I'll just move this to the front. Okay, ground is installed. Now as you can see, this here pushes in nicely, and the biggest issue is that I still need to get maybe 1 millimeter off here at the back. Let me actually see. So either I angle it this way, do have a little bit of space there, because I have to redo the bolts. I didn't do that yet. So that still sits in there. Okay, this is great. Time to hook it up on the other side. Alrighty, time to power it up and feed it some wire and see if that works nicely. Oh, it's running in reverse. Alright, time to switch that power cable. I guess I got those 2 inverted there. Attempt number 2, switch the power cables around. And now they're running the right way. Huh. There's always something, eh? So when you take a look at this, it's instantly visible why this doesn't work. This one here has an 8 in it, and I only have 10 and 12. So the wire is literally too thin. All right, so for the benefit of making progress, I switched the 0.8 millimeter wire for 0.9 millimeter wire because that will feed. Okay. There we go. Nice. Time for our comparison. So before I timed 3 values, lowest IPM, medium and highest IPM, about 6 seconds each. Okay. Let's compare them here side by side in a second. So this here was my original sample. And the thing that I found really interesting is between the half and full speed, you can see, it's maybe double the size, but the lowest speed gave a 59 IPM here produced less than 5 centimeter difference. So those were totally different. And now when I take this and compare it to 1 for 1, the longest segment here, it is quite a bit longer. That's something that I have to go back to programming. Okay, let's put them. The lowest IPM are also a little bit longer. So I'm fairly certain that this as it exists will not immediately work. I'll give it a go nonetheless. Let me actually switch to synergic mode here for a second. Oh, was I in synergic mode? Let me actually do one more 6-second test here. Interesting. Interesting indeed. Okay. So this is really interesting. When I feed in synergic mode, the wire I get out is basically identical so to what I had before, which means MIG manual and MIG synergic feeds differently even if I have the same IPM. This makes me optimistic, given that this was the same length, that it will maybe work after all. How great would that be? And obviously keep in mind, I don't really know what I'm doing. Alright, this is literally the first welding with a 4-drive roll wire feeder. So, let's see how this actually goes. I have plenty of scrap floating around, so I just tag something and then play around a little bit. So this was just a very brief test. So let's take a look. I actually think that these welds, bearing my skill as a welder, look freaking great. So I will play around with slightly different settings to just see if this is just medium range, or if I can weld thin and thick with it too. But honestly, I don't notice a difference, which is exactly what I was aiming for. This makes me very optimistic that this hack is actually something that will work for me long time. So how great would that be? So this one here, that was the pulsed MIG, and this one here and this one here is just on the flat surface. And you can see one thing, and you can hear it actually. The 75 watt wire feeder is a little bit slower in spinning up, and I was anticipating that, but this is just the very beginning of the weld, and once you get going it actually looks like it did before. And this means two things for me, and I was actually expecting that. Number one, it means that it takes a second longer on the SF390 to get to the correct speed setting than on the SF150. Again, totally expected, because I have a 75 watt motor in there and the old one was a 50 watt motor. And the second thing it means is, once I'm welding, takes about 1 or 2 seconds, it's exactly how it was before. Like, it sounded great, it welded great, which means for me, I will totally keep this in there as a prototype. And what I would need to do to make this really bulletproof is I basically would need to add reverse reading of the pulse width from the 24 volt rail that powers the motor, and then use that to control my own motor driver, which basically means the PCB needs to get its own 24 volt rail, which is uninterrupted, and I need to add a little bit of ICs in there to do the necessary motor control and reading the 24 volt, just the pulse width modulation, and then I can basically match the old speed 1-for-1. The current design here is a PCB that just does mechanical gear translation, and then it fakes the signal it sends to the onboard computer to say I'm really rotating, at whatever speed it should be. And this is important because I need to keep the distance per rotation identical. And the old system had a different gear ratio, it had different drive roll sizes. And if the new system with different gear ratio and different drive roll sizes has to spit out the same amount of wire per encoder signals, then obviously I have to do some translation to make it think that it's feeding faster or slower, right? And this is basically why I have the IC on there. And that works after the initial start phase, which means great, the math seems to be fine. The only problem is the start phase takes like a second to ramp up to the correct speed because the motor is a little bit slower. But to me, I think that will work great still. I can live with it for now because pulsing, I use it quite frequently, but only in the 8th inch material size right now, because that's most of the animal feeders and stuff that I'm building. And it worked great for that setting, actually. Surprisingly, I didn't feel a difference. And for the thicker material, I mean, putting the machine to its highest output, that worked great again too, without any stuttering and starting. So I'll just finalize this and bolt everything down, and then run this for a few months and let you folks know how this goes, you know. But for now, I think I'm really happy with this, or rather, I think I could be. Oh boy. All right, with that demo out of the way, let's quickly jump into Fusion 360 because I want to show you what went into actually making all of this happen. There's an STM32F303 in here. I think this is a great IC MCU, which in this case only takes inputs from this AS5047P. This is an magnetic encoder. What this means, basically, just below it you mount a diametric magnet, and where the magnet field basically runs radially, and as the magnet rotates, this chip here can read the rotation. The output of this here runs through quadrature AB signals to the IC. The IC then does the gear ratio math, which is literally just, you know, a big division if you want. And every so often it toggles the encoder output, and the encoder output is directly fed over to the Stel PCB. So this is, in a nutshell, literally everything that sits in here. You can see that the PCB itself also isn't quite complicated. It's a 4-layer PCB, but it's only 4 layers to protect it against EMI. And this is also why I added that metal shield at the bottom, because the motor of the wire feeder obviously creates a magnetic field as it rotates, and I have to protect the magnetic encoder from that, right? And the only way to do that is pretty much by having something that saturates and takes that magnetic field. So this is why I put a thin metal bending bracket below it, which I bent from thin metal with pre-printed shaping tools, right? And then obviously in here you can see this one here is just the output, and then I have like a debug and programming port here, which is Tech Connect. God, I love Tech Connect. It's really great. And this thing works great. It's running at 64 megahertz to make sure that it never misses a pulse. It makes me very optimistic that I actually have something which I can just continue to use for a while. And whenever I get fed up with that 1 second cold start issue, I'll just take another 50 to 100 bucks in the hands, order some ICs and custom PCB from China, and have a motor driver on there. If you've attempted to do something similar, I would love to hear your opinion on, you know, should companies be more supportive of these kinds of modifications. This is my first time modifying a welder, and I think I say this in every video these days. I have no idea what I'm doing. Thank you so much for watching. You have a great evening.